Hi everyone, my name is Aborno Isaac Berry from Berry Science Lab, and today, welcome back to Complex Analysis. This is lecture number 4, and today we're talking about the Cauchy-Riemann theorem. So, what does this say? Well, remember that the complex numbers are similar in many ways to R2. And we also know that any function from R2 to R2 has a Jacobian. df is equal to the matrix partial x fx partial y fx partial x fy partial y fy. So this is the Jacobian. And you can't define a universal derivative that exists for any partial differentiable function for a two-variable function. But in complex analysis, these things become a whole lot nicer. Recall that we can actually assign meaning to the expression f prime of z naught by setting it equal to the limit as z approaches z naught of f of z minus f of z naught over z minus z naught. The issue with any general R2 to R2 is that dividing by a vector has no meaning. But when complex numbers transforms our vectors into, numbers that we can freely divide by, then this derivative has all the meaning we need from it. But how does that relate to this function's actual Jacobian? Well, very deeply. And the Cauchy-Riemann theorem actually unveils very surprising results about the Jacobian that allow us to basically forgo it entirely. So what does it mean for a function to be analytic? Well, of course, for this to exist, but can we phrase it in terms of the Jacobian? Well, sure we can. No, that's blue. So, what does it mean to be differentiable or analytic in terms of complex analysis? Well, it's similar to what we consider differentiable in R. If for any epsilon is greater than 0, we can find delta as a function of epsilon greater than 0 such that the norm of x minus x naught, y minus y naught is less than or equal to delta implies that the norm of f of x minus f of x y minus f of x naught y naught plus df at x naught y naught multiplied by the vector x naught y naught is less than or equal to epsilon times the norm of x minus x naught y minus y naught. And similarly, if you wanted to simplify this to 1D, this is just f of x minus f of x naught plus f prime of x times x naught. That norm has to be less than or equal to e times the distance between x minus x naught. In fact, this would be single because absolute values, not norms. So, as you can see, there's a very close analog between the two. Now, how do we know that how does this relate to the Cauchy-Riemann theorem? What does the Cauchy-Riemann theorem actually tell us? Well, it's going to tell us two very big things. Partial x of, okay, let's write f of x plus iy as u plus iv. Both of these are functions of xy. Then this is telling us partial xu is actually, let's just put it the blunt way. Partial xf is equal to minus I partial yf. And not just that, partial xu plus I partial xv is equal to partial yv minus I partial xu. This is what the Cauchy-Riemann theorem tells us. And in that way, it's essentially telling us partial xu is equal to partial yv, and also partial xv is equal to minus partial xu, which is definitely not true for any general function. It's basically reducing the Jacobian for a complex function to this. Wait, hold up. I think I'm stupid. This should be y. So partial xv, or even partial yu.
Don't block everything you write.
So you can actually simplify it to something like this. And notice the resemblance to something like, for example, the rotation matrix. Okay. Now back to what we were saying. How do we actually prove this? Well, we're going to take the definition of f prime of, oh, and one last bombshell, this is directly equal to f prime. So how do we prove this? Well, let's write out f prime of z naught first, or just f prime of, f prime of z naught. It's the limit as z approaches z naught of f of z minus f of z naught over z minus z naught. Pretty simple definition. Now, I'm going to take z such that, let's say x naught, y naught, z naught is this point on the complex plane. So then we're going to go in two axes, along the real axis and imaginary axis. So first, we're going to take some random point with the same imaginary component but different real component, and then we're going to take another point with the same real component but different imaginary component. And we'll see what we get out of it. So f prime of z naught is equal to the limit as you approach it. Let's pick one randomly. Let's start with this one. As here, just x approaches 0, because that's the only way this point can approach z naught. The limit as x approaches 0 of f of x comma y naught minus f of x naught comma y naught divided by x. Since z is just x plus I y naught, and z naught is minus x naught minus I y naught. Wait, so shouldn't it be x minus x naught? And actually, as you can see, this is essentially just taking the partial derivative with respect to x. As you can see, partial x of f is equal to the limit as x approaches 0 of f of x comma y naught minus, x approaches x naught of, so this should be x approaches x naught. Oops. f of x comma y naught minus f of x naught comma y naught divided by x minus x naught. These two are the exact same. Partial x of f is the exact same as f prime of z naught. Now what happens if we go from the other direction and try to find partial y of f? Well, we get the limit as y approaches y naught of what? Well, f of z, which is x naught plus iy minus f of x naught plus iy naught over what's here? Iy minus iy naught. So you can factor out the I and just get y minus y naught. So it looks like this is 1 over I, a constant, or just negative I, multiplied by partial y of f. So we have right here in front of us that partial x of f is equal to minus I partial y of f. And then we can expand it out and compare the individual real and imaginary components to get the full Cauchy-Riemann theorem. And this is massive because it's the first site of analytic functions that are differentiable everywhere, being so much nicer and having so many more constraining properties that we can use to say really great things about them than just regular differentiable functions do in real analysis. Complex analysis is a lot nicer than real analysis, and we'll continue to see that as we keep studying more properties of analytic functions next time. Thank you everybody for watching, and we'll see you in the next one.